So the next spectrum one we'll look at is that of an alcohol, and this is the original one we kind of took a look at when we were introducing the chapter. So, but this lovely, big, broad, pretty smooth peak over here is the OH of an alcohol. So, and as we said just a little bit ago, that it is different in, both how it looks as well as where it shifts than the OH of a carboxylic acid over here. So if you notice, this one's centered closer to 3,000. So, but for the alcohol, it's centered closer to somewhere usually between like 32 and 3,600. So there's also something you should know. It's so broad typically due to hydrogen bonding. So hydrogen bonding, it turns out, weakens this bond. And so when this molecule is involved in hydrogen bonding with some of the other molecules in the solution, so it weakens the bond, also gives you kind of an average of energies. You get a variety of energies that are possible. So, and as a result, you get a broad peak that's also shifted down a little bit. So if you might make this solution a little bit more dilute, so there's not as much hydrogen bonding going on, what you'd find out is that this peak might not be so broad, and it would probably end up getting shifted to the left. Again, hydrogen bonding gives you some average possible energies for the bond vibration, but also weakens the OH bond a little bit as well. So in dilute solutions, it'd be a little bit further left and probably nowhere near as broad. Just an FYI. But hopefully here you can tell the difference between the alcohol and the carboxylic acid. So if you also look at the spectrum on the left here, we've got right here, notice again to the right of 3,000, these are sp3 carbon hydrogen bonds. So, and this spectrum corresponds to some sort of what we call aliphatic alcohol, an alkane alcohol. And that's about all we determine. Everything else is to the right of 1500, and therefore in the fingerprint region. So again, we're never going to get a complete structure from the IR typically, but I would know this thing's an alcohol and an alkane, and I'd know that it's not a whole bunch of other functional groups as well. So in this next example, I want you to see the difference between an amine and the alcohol we just took a look at. So in this case, they both have peaks down in the kind of that 32 to 3,600 range. So, but you'll see some differences here. So if you recall, the alcohol here is this nice broad peak most of the time. So whereas the amine's usually not quite so broad, it's usually still generally classed as broad, but it's not anywhere near as broad most of the time. And you might see either one peak or two peak, depending on how many hydrogens are bonded to your nitrogen. With two peaks, we have what's called a primary, either amine or amide. This one's going to be an amine. So, and that's because the nitrogen's bonded to two hydrogens. So with a secondary amine, only bonded to one hydrogen, you'd only see one of those two peaks actually showing up. So in this case, a lot of students get confused at this level. Primary, secondary, I'm confused. And so it turns out primary and secondary is determined not based on how many hydrogens the nitrogen's bonded to, but how many carbons it's bonded to. So with this nitrogen being only bonded to one carbon, that's a primary amine. With this one being bonded to two carbons and only one hydrogen, but two carbons, that's a secondary amine. So if you're confused where that classification comes from, that's where it was coming from. So, but these are the NH peaks, and I'm just going to say NH2 in this case, since there's two peaks, two H's. So right over here, if you look again, right where 3,000 is, that's largely to the left of 3,000. So these are your sp2 CH bonds also showing up in this. And if we have sp2 carbon hydrogen bonds, that either means alkene or aromatic. So in going off over here, we've got a couple of peaks right in the 1,500 to 1,600 range. So, and that's a giveaway, you've got a benzene ring. So it turns out your benzene carbon-carbon bonds generally show up with a combination of 1, 2, or 3 peaks in kind of that 1,500 to 1,600 range. You'll also see some much smaller peaks typically in this range, but I don't usually like identifying benzenes from that, but rather from these peaks in the 15 to 1600. And when I say 15 to 1600, one thing you should note, it usually means a little lower than 15 to just a little bit higher than 16, a little bit of a buffer on that. So, but again, you might see 1, 2, or 3 peaks depending on the specific aromatic compound. So the last example we're going to take a look at, I'm going to use to help you distinguish between an alkyne and a nitrile. And if you don't know what a nitrile is just yet, a nitrile has a carbon-nitrogen triple bond here. So, and in this case, alkyne has a carbon-carbon triple bond. So, and you might recall that those triple bonds show kind of right up in here in this 21 to 2300 range. So, if we look at the differences here, there's two types of alkynes. We got a terminal alkyne and an internal alkyne. And if you recall with this internal alkyne, if we showed an example of IR inactive bonds involving an internal alkyne, and if R1 and R2 are identical groups, this thing will be perfectly symmetrical. It'll have no dipole moment, and stretching it, it'll still have no dipole moment. And so as a result, so your carbon-carbon triple bond would be IR inactive. Well, it turns out even if R1 and R2, again, still being carbon chains, even if they're not identical, so it turns out this thing has such slight polarity associated with it that you don't ever typically get a strong signal for an internal alkyne. You might get a super small signal in that 21 to 2200 range, but oftentimes it's just not even visible. So even when it's not perfectly symmetrical, you're usually not going to see the internal alkyne, so we'll just kind of ignore it for this comparison. But if you look at the terminal alkyne here, so this molecule actually is polar now with a carbon chain on one side, a hydrogen on the other. So, and when you stretch it, you definitely change the dipole moment, so it's definitely going to show up. And again, this generally is going to show up somewhere around 2200. So, but for your nitrile, it also is going to show up generally somewhere right around 2200. Now, it's a slightly more polar bond. It turns out it might show up just barely further down, you know, slightly higher absorption, higher wave number. It also has a more polar bond, so it might be a little bit stronger absorption, but not a ton there either. And if you don't have them side by side, it might be hard to tell. So the big difference between them then is with the terminal alkyne, you're always going to get this additional peak right here for that sp carbon-hydrogen bond that shows up at 3300. So if we look at our spectrum at hand here, again, we've got this triple bond right here. And again, whether it's carbon-carbon or carbon-nitrogen, immediately I look over at 3300, and we have this nice, lovely, strong absorption. That's the SPCH. And being the SPCH, it tells me I've got a terminal alkyne, not a nitrile. And so this corresponds to a carbon-carbon triple bond, not a carbon-nitrogen triple bond. So the other signals, again, left of 1500 that we might have to identify outside the fingerprint range is just these guys right here, and being just to the right of 3000, not just to the left. These are sp3ch bonds. So there's an alkane region in this molecule as well. So this thing is a terminal alkyne and an alkane. And again, we would never get the whole structure here, just the functional groups we're ultimately determining about our compounds.